we shall start our discussion on pumping system design today. And if we try to recall, in the last a few lectures we have discussed several issues related to pumps, their both design as well as operational aspects. So, which is most important is in the context of pump operation is the system design. So, whenever a pump or pumps are installed in a pumping station, it is very much essential to know the system resistance. So, basically what is done before procuring any particular pump, it is necessary to have information about the system in which pump is going to be installed. Now, information is basically the geometrical consideration of the pumping systems. I can say if there are multiple systems, if the pumps are installed in a house in a given pumping station, we need to know the elevation of the pump house in which wherein pump is installed, the elevation of the discharging points, piping layout, number of accessories like valves, fittings include bends, elbow required for the smooth operation pump or pumps. Now, if we try to recall, we have discussed about, so if we talk about the for this particular topic, we shall be focusing on the design of the radial flow pump, pumping system rather. So, if we try to recall, if we consider radial flow pump, or pumps. Now, we have seen that we can obtain the pump characteristic. So, this is also known as H cube characteristic, or it is known as pump characteristic. Now, this H cube curve, which is the pump own characteristic, should be supplied by the pump manufacturer. So, we have seen that we should look for this type of characteristic wherein the curve should have a continuously drooping characteristic. So, with increasing Q, if this is Q axis, this is H axis. So, with increasing Q, there will be a gradual reduction in head that will be developed by the pump. So, this is pump own characteristic. Let me tell you, radial flow pump always works against the system resistance, the resistance of the system in which pump is installed. So, this is pump own characteristic. Now, we really do not know what will be the operating point, and that operating point will be fixed by the system resistance, the resistance of the system in which pump should be installed. And we have seen that if we talk about a pump, and this pump is radial flow pump, and it is used to discharge water in a tank which is located say h2 distance above the pump axis. So, this is pump axis, right, and it is taking water from the sump. So, this is the discharging point. Okay. Question is, so we can understand now there are two different issues that I am going to discuss today. For this particular topic, that is system design, I will be taking two classes. There are several issues that should be taken into account when any system designer is looking into the precise or accurate design of the system. There are two different cases. If the pump is, I have discussed this part whenever I have discussed about the NPSH, if I can recall correctly. So, there are two different cases. Say the case 1, when the pump is taking water from a tank where water level is h1 distance below the pump datum, pump axis. So, this is the water level and we have seen there will be strainer. So, this is the water that, and this is called suction tank. So, this is suction tank. Okay. So, in this case you can understand. So, this is pump datum that is the axis of the impeller. So, that is commonly termed as the pump datum. Let me tell you again, pump datum is very important term which is known as the axis of the impeller. So, now, so this is pump datum. Okay. In this case you can understand, I did not show, you can see at least from the schematic depiction that there is a vein which is required 90-degree vein, again there is another vein over here, another vein over here. So, you can see that taking water from the suction tank to supply this water to the discharging point, we need to have pipeline. Length of the pipeline will depend upon the piping layout, the that our system designer will decide. Also we can see there is a strainer and 3 different bends of 90-degree, right. So, that will be properly designed by the system designer to make it very accurate and what I can say economic design. Economic, the word I am using economic because you can understand the presence of number of bends valves will definitely increase the resistance that the water or any liquid will encounter while flowing from this point to that point, and that resistance should be handled by the pump, and that is the sole objective of having this pump over here. So, you can understand the resistance that the water will experience, water will face for its transportation from this point to that point will be taken care by the pump, and that is why pump is there. Water cannot easily go from this point to that point, and that is why this pump is there. So, we need to have energy input, energy addition, and that is done in the pump. So, basically you can understand here the total head that will be developed by the pump will take care all those. What are the components specific to this particular example? You can understand the total head that will be developed by the pump will include this static height H1, this static height H2, friction loss both in the suction pipeline, delivery pipeline, minor losses due to the presence of strainer, minor losses due to the bends which will be required for the smooth operation of the system. So, if we try to recall, I did not draw anything. So, this is pump own characteristics, let me tell you. So, this is pump own characteristic and that will be supplied by the pump designer. But before the pump designer start designing the pump, he or she should know, rather he or she must know about the system resistance, and that is what I have discussed, because he or she should know the NPSH available, right. So, basically NPSH available is the quantity and that will depend on the thermodynamic parameters of the liquid thermodynamics, thermodynamic parameter of the ambience in which the pump should be installed. So, basically those information, right, the system design, total head that will be developed by the pump together with the amount of water will be handled by the pump. So, again I am telling these two quantities are very much important. First of all, head that will be developed by the pump, and cube will be discharged by the pump. So, these two quantities are very much needed at the designer end, without which designer will not be able to design the pump, because he or she needs information about these two quantities. Fine. Now, what we need to know? We need to know the operating point, but that operating point will be fixed by the system resistance. Again I am telling, radial flow pump or pumps are always working against this system resistance. So, particular for this, and this system is known as negative suction. So, pump is running under negative suction condition, maybe here atmospheric pressure is acting. So, that is the driving force for the liquid to be transported from this strainer to the inlet to the pump. So, this is the driving force. Anyway, so for this particular case, so case 1 schematic I have drawn in the previous slide, that is when pump is running in negative suction mode. So, basically pressure at this point. So, if we give a point over here, that is inlet to the pump impeller, at that point is vacuum pressure. So, pressure less than the atmospheric pressure, right. So, I mean you can understand that is created by the pump itself, that vacuum is created by the pump itself. The moment when there is a pressure difference between the strainer and this particular point, only then liquid will start flowing from this point to that point. Mind it, when liquid is flowing from this point to this point, then that liquid also will encounter loss due to friction and other minor losses due to the presence of strainer and bends. Okay. So, for this particular case, when pump is running in negative suction mode, then total head to be developed by the pump is capital H, that is the head loss in the suction side plus head loss in the delivery side. Right. So, if we give this is small h1 and this is small h2, h1s, h2d, h2d. Okay. So, that is basically that is the total head that should be developed by the pump. Now, if we try to look at this particular two components, that is the head loss in the suction side as well as the head loss in the delivery side. See, if we go back to the previous slide, we can understand that this is the static height difference h1, but we have written that is h1s. So, this is h1s. So, this is h1s and this h1s is not equal to h1. So, basically this h1s will be equal to h1 plus you have studied fluid mechanics. So, you can understand when liquid is moving from this from strainer to the pipeline. So, basically if we try to draw a zoomed in view, so basically this is the strainer, I mean if I write here, so this is the strainer and this is the pipeline. So, you can understand as if liquid is passing, there is a sudden contraction. So, there will be losses, there will be a loss, not losses, there will be a loss. So, basically when liquid is just entering to the pipe suction pipeline from the strainer, and this flow scenario is mimicking the flow through a sudden contraction. So, due to the sudden contraction effect, there will be a loss. Also, liquid is again passing through the pipeline, friction loss will be there. The presence of bend also will provide certain amount of loss to the system, and that will be taken care by the pump. So, that is why I am writing this H1, that is the static height. So, this is static height plus HFS. So, this is friction loss in the suction side plus minor losses HS minor. So, you can understand that the static height is there because we need to pump liquid from this height to that height. For that we need to impart energy to the system, that energy should be imparted by the system, so that to the liquid, so the liquid will come from this point to that point. Then the friction loss while passing, rather moving the liquid is getting transported from this point to that point, plus the minor losses due to the presence of bend and also loss due to sudden contraction. So, we cannot avoid it. If we cannot design all these minor issues, what will happen? Maybe after installation of the pump, whenever pump operator will try to operate the pump, pump will not work. So, I will discuss that issue again. So, you can understand the total loss in the suction side is this. Basically static height, you know, that is the static height we need to overcome. Frictional losses HFS, that is equal to F suction side, length suction side, diameter of the suction side, Vs square by 2g. So, that is what we have studied from fluid mechanics course, Darcy-Weisbach equation. Recommended speed of water through the suction pipeline, that I told you that speed should be at least one, I mean slightly less than the velocity at the delivery side, and that is why this is required, that we have discussed. Now, so this I am talking about for the case when pump is running in the negative suction condition. If the velocity becomes very high, then perhaps the head that will be available at the inlet to the impeller will not be able to overcome the minimum head required to overcome the cavitation, right. So, that is why the velocity in the suction line is kept at least one size, I mean one, not one order, but slightly less than the liquid velocity which is there in the delivery side. So, F friction factor, that you cannot directly use from the 64 by RE, because that is for laminar flow. As I told you that the flow is highly turbulent when liquid is passing through the suction strainer to the pump inlet. Recommended velocity is almost 2 meter, 2.5 meter per second. So, at that velocity, considering diameter of the pipe, flow is highly turbulent. So, what we need to do, knowing the surface roughness of the pipe, we can easily calculate it, and by calculating Reynolds number we can calculate it from the Moody's diagram. So, we can calculate HFS, fine, and then which is very important, HS minor. So, that is the minor losses. So, losses due to the presence of bend, losses due to this effect, that is as if the flow is mimicking the flow scenario of through a certain contraction. So, and also again there will be sudden expansion. So, liquid when just entering to the pump impeller, again there will be sudden expansion. So, all those losses. So, if I try to write that, minor losses should be taken into account. So, you can understand, if we just try to, you have to design it properly, the losses in the bends, losses in the knowing the angle of the bend, also the diameter we can calculate, also we can calculate the sudden contraction and sudden expansion. So, we need to calculate, if it is sudden contraction, then this is 0.5 V s square by 2 g plus, that is the loss in the bend, that is loss in bend, plus loss in bend, plus, as I told you that this particular flow will mimic as if the flow is having sudden expansion. The moment when liquid is entering to the pump impeller, then that will be flow, I mean there will be loss due to sudden expansion, and that is V s square by 2 g. So, basically this you have studied from the fluid mechanics course. So, you can understand, because I am not going to discuss all those aspects, but you can easily get it from any good books, any good book on fluid mechanics, undergraduate textbook. So, you can understand that here the area will be much higher than the area of the pipeline. So, basically 1 minus A 1 by A 2 square will be equal to 1, and that is why this is V s square by 2 g. So, basically if we try to write it in terms of, you can understand it will be 0.5 V s square by 2 g, and this loss in bend also a function of V s square by 2 g. So, eventually if we try to write that it is a some constant into V s square by 2 g. So, basically if we try to write that H s minor will be some constant into V s square by 2 g. Okay. So, basically you can understand this is also constant, you can easily calculate it. So, this is k V s square by 2 g plus H 1. So, total loss H 1 s. So, H 1 s will be equal to H 1 plus, that is, say this is k 2. So, this is k 1 plus k 2 V s square by 2 g, and this term you can write as if this is equal to k 1. Okay. So, you can understand the total, this way you can calculate total loss, I mean friction loss, I mean head loss. Similarly, we also can calculate head loss in the delivery side, right. So, head loss in the delivery side will be equal to, that is H 1 d will be equal to H 2 plus, again you can see from the schematic depiction there will be bends and eventually there is a certain expansion. So, if we just write, I mean we can write that is k 3 into V d square by 2 g. So, basically we know V s and V d, and that is obtained because, so V s equal to q by pi by 4 d s square and V d equal to q divided by pi by 4 d d square. So, d s and d d are the diameter of the pump suction pipe and the delivery pipe, and as I told you that suction pipe is kept at least one or one size higher than the delivery size. So, that those aspects we have discussed in detail in previous classes. So, basically now you can understand that particular this configuration, if the pump is running in the negative suction condition, then the total head developed by the pump will be equal to total head. So, the total head H, that is basically H 1 plus H 2 plus k 1 plus k 2 into V s square by 2 g plus k 3 V d square by 2 g. So, if we try to mark it, so this is the total head that will be developed by the pump. I will be now discussing that this is the total head that should be developed by the pump pertaining to the system, and pump is running in the negative suction condition. If there is a mistake in calculating this H1 and H2 is fine, we know in this term, then the system in which pump will be installed may not work perfectly or correctly. So, it will give trouble, and the pump operator, in fact the system engineer will face that, and again he or she needs to contact the pump designer. So, which is very important, by knowing this H and by knowing this fellow cube, so basically that is the system requirement. That is the system requirement. This H is also the system requirement. So, knowing these two quantities Q and H, if these two quantities are given to the pump designer will design the pump and he or she will provide this H cube curve. What we need to do next? We need to know the system resistance. You can understand very quickly, Vs is function of cube, Vd is function of cube. So, eventually we can write this H equal to H1 plus H2 plus K1 plus K2 plus K3. I can write this term is equal to K4 into Q square, right. So, I am writing this is almost equal to. You can understand that this I can write this because Vs and Vd, Vs is function of Q, we can write Vs and Vd in terms of Q from the above expression. So, eventually we will get like this. In that case, we know what will be the system resistance, right. So, the total system resistance for this particular case when the pump is running in the negative suction mode will be this. If we try to draw this curve on this H cube plane, maybe you will be getting a curve like this. Eventually you can understand this is the equation of a parabola, but not passing through the origin, right. So, we can easily plot it, we can superimpose this curve on this particular curve, and this is the system resistance or system characteristics, system characteristics. Okay. Now, you can understand, and this is the static height. Okay. So, you can understand the system resistance now fixes off, rather it intersects with the pump own characteristic curve at a point, and that is the operating point, and the head discharge corresponding to this operating point are the head and discharge that we will be getting from the pumping system. So, this is Q operating and this is H operating. Okay. So, you can understand we will be getting Q operating and H operating from the system resistance, because system resistance will fix up this point, right. What I would like to discuss over here, if we really do not know, if we have calculated this system resistance wrongly, if we have calculated the system resistance both in the suction side and delivery side wrongly, then perhaps this K4 value will be changing. So, this magnitude of this constant K4 will essentially depend on the accurate design of the system. If we cannot, right, initially we have to give this two data to the pump designer. So, knowing the value of H and Q, pump designer will design the pump and he or she will supply this curve. Question is, if the system designer he or she did some mistake while the total resistance both in the suction side and delivery side was calculated, and now if that is the case, then what will happen if the system resistance is more? Let us quickly review. if I try to draw using a different color, say green color, if the system resistance is more, there is no problem with the static height, because that someone can easily measure, right. Someone can easily measure H1 and H2. So, there will not be any mistake in doing that calculation, but the mistake will be there while calculating the friction loss and the minor losses. What is most important, that is the minor losses, because you really do not know the loss in the bend, that is why I could not write the mathematical expression. What is done in practice normally, instead of calculating the minor losses following this equation, it is taken 50% of the total losses to keep the system in a safe mode. So, basically in practice, in industry practice, what is done, the minor losses, the amount or the total minor losses are considered to be 15% of the total losses, because it is very difficult to calculate due to losses in bend. So, you need to go for the computational fluid dynamics to calculate the amount of losses. So, that is not always true. So, basically if that is not taken care, what will be the problem? Now, depending on the magnitude of the minor losses, and if that losses has not been calculated properly or correctly, what will be the problem? Problem will be maybe this curve will be steeper, right. So, maybe this, in that case you can understand this will be the operating point. Now, what will be the problem? See, that static height is remaining same, but the minor losses which was calculated initially, and based on that calculation total H was calculated, and that total H was given to the pump designer. Pump designer, based on those input parameters, he or she has designed the pump, and this is the H cube curve. Now, as I said you, the system resistance which were calculated initially are not the correct. So, basically are calculated by mistake. So, basically if this is the actual or corrected system resistance, you can understand this will be the operating point. So, what we will get, our expectation is that we will be getting this amount of flow rate, instead we will be getting this amount of flow rate. So, basically again this is cube operating nu, and this is H operating nu. So, this is H operating nu. I have no problem, maybe the system will be getting less amount of flow rate, that is again very problematic to the system. Required amount of liquid will not be supplied by the pump, though the pump is supposed to be work accurately, but due to this calculation problem will be there. Second thing which is most important to discuss, which is most important to know, see this H operating nu, the head against which the pump will be working is very close to the shut off head, because that is the pump own characteristic, you cannot change. So, when the pump is designed, blade angles are designed, impeller diameter is designed, pump casing is designed. So, this is fixed, shut off head is fixed, we cannot do any more changes. What will be the problem? The head at which the pump is operating, the pump is supposed to operate at this point, but that is not the correct system resistance, and in real practice pump is experiencing that is the system resistance, and this will be operating point, and head corresponding to this operating point is very close to the shut off head. By mistake, if the pump operator closes any valve in the delivery side slightly, this curve will be slightly shifted again. So, this curve will be shifted slightly like this, and this head will be now the shut off head. What will be the problem? You will be hearing one common term, and that common term is used industry experts, the engineer which are responsible to look after this system, use this term very commonly, that is pump tripping. So, pump will trip. Why? You can understand the head which is close to the shut off head. Now, why pump will trip? Because the pump trip will be there, because the input power to the pump will be equal to, that will be supplied by the electric motor, and that will depend upon the rho cube G H, right. So, basically you can understand, so this is the rho cube G H, right. So, this is P out, not P in, I am writing. So, this is P in. So, why pump will trip, let me tell you. So, if we try to write the P output equal to rho cube G into H. So, now if H is becoming close to sort of fade, then output power, that is the power required to drive the, so pump output power and pump input power, right. So, this is the output power, and to get this output power, the input power should be more, because some amount of losses will be there, and that is why the concept of overall efficiency is there, and we have discussed this part. So, you can understand this output power will be very close to the input power if H is calculated wrongly. So, eventually what will happen if we go to that slide. So, when by mistake if the operator closes the valve suddenly, and that is commonly done in industrial operation. So, what will happen, this operating point will be very close to the shut off head and pump will try to run at a shut off head and pump will trip. The reason is the output power will be almost equal to the input power, and almost sometimes what is happened, that output power will be more than the input power that will be supplied by the electric motor. So, basically everything is designed based on the Q and H. Now, whenever pump is designed, accordingly electrical motor that will be used to run the pump is also designed. Now, in any case, if the amount of input power, the demand by the pump from the electrical motor is beyond the motor capability, then pump will trip, and to avoid that, it is very essential to design the pumping system accurately. So, this is what I was thinking to discuss. So, this is what I have discussed in the context of when the pump is running in the negative suction condition. There are different other aspects in which the pumping systems are designed to run using positive suction mode. In that case, I will be discussing that the head required, the head loss in the suction side will not be there, and perhaps the problem associated with the pump tripping somehow can be prevented. Not only that, another advantageous feature of this particular arrangement when pump will be running following the positive suction mode is that the onset of cavitation also can be avoided. So, the issues and also the system resistance in the when the pump will be running following the positive suction mode will be discussed in the next class. With this, I stop here today. Thank you.